Thank you. Let me start my presentation. Good. So this demo is actually more, it's about using OpenEO for doing analysis, but it's in fact still a prototype, the integration of the layers. That's an important remark. So it's not readily generally available to the public yet, but we do show the possibilities. So just to explain actually what OpenEO is, it's a cloud-based processing service that aims to provide very simple data access and processing. So in this case, you will not see access to files and products and catalogs. We all hide that behind a web API, but we also offer Python and R libraries in addition to the web API, because as a data scientist, those are often the languages that you want to be working with. We also have a set of online tools that you can use to explore, for instance, the available collections. But most of the demos that I will show today are more in Python from a Jupyter notebook. So why did we create OpenEO? This is a slide from Isa. It's about the data management burden. And actually, you saw some examples of it today. So you usually, for your study area, identify the tiles. That's through the typical catalog search. Then you either download it, or luckily nowadays, sometimes you can even do direct queries to the buckets using raster.io and so on. But in any case, you try to fetch the data locally, which you then have to pre-process. Sometimes you can download the subset. Sometimes you first download the whole product and then do subsetting, then apply algorithms and release your product again. Of course, if you need to do this at a large scale, then this also involves doing some parallelization. So defining tasks that you then want to, on some kind of cloud infrastructure, parallelize or on your local machine, run on multiple CPUs. So again, that's a process that involves some knowledge on how to actually do that. So it's not always simple anymore. The data access and processing of these very large data sets like this one. Other things that we do, so we have this OpenEO API, and these are kind of like all the things that we try to hide behind the API. So everything, you could say IT related, but also related to standards, metadata, file formats, even some of the FAIR principles, the whole scaling out. We try to hide that behind our API so that a data scientist can focus on other things, like really the specific thematic domain you're working in, doing some rapid prototyping, applying AI. So those are still things that you would be doing on your side. And we try to take care of these other things. So where is it relevant, to give you an idea? Also, for instance, when combining with other data sets. So in OpenEO, we not only include the EA data sets or the HRL data set, we actually already offer over 60 plus data sets. And it allows you to easily combine with that data. So really, creating workflows that combine more than one data set. You can then usually start on a small area to test out some things, then you can maybe scale up to a country or to a full continent. And so you can really have this scalability all with the same code. I think this was also a question I saw popping up in the Q&A. The processing then happens cloud-based, without actually noticing too much of it. And you can even apply your own custom Python code. So based on X-array NumPy, you can inject pieces of Python code so that you're not limited to the processes that we have implemented in OpenEO ourselves. You can also make use of the rich Python ecosystem and its libraries. So those are some of the things you can do. Yeah, of course, as a warning, this is a prototype. What does it mean? Currently, the cluster we run on is not very big. It's rather small. We haven't even integrated all of the HRL data yet. In fact, only a few bands and data sets. And also, yeah, quality checking is limited or has been limited. It's really a prototype for this webinar. So let me switch here to the actual, yeah, more like Jupyter Notebook demo that we've prepared to show you what it looks like. It's a Python package, or at least the client-side package is something you need to install. Here we did it through the regular pip install OpenEO. That installs the client side. Of course, most of the work happens on the web service. So the client is also relatively easy to install, and you can import it and look at the version to make sure that you have the latest one. It's a web service, so we also always need to connect to something. This one runs on the same cloud that hosts the data set, so that the processing is close to the data. That's an important principle. And we authenticate. I authenticated before, so here it actually happened quite fast. If you do it for the first time, then you actually need to log in, of course, otherwise it wouldn't be secure. The first thing we want to do here is download a very simple data set. So yeah, here again, I put my setup of the connection. I specify the collection that we want to download. Here it's seasonal trajectories, and I give a spatial temporal range. So date range and the bounding box that was specified here. And then actually this one returned in 10 seconds as a nice netcdf file. Netcdf is convenient because X-Array can load it, and you see that the PPI is returned here as well as the Q flag, and also the time dimension of the data is nicely decoded by X-Array, so that with one plot command I can plot a few of these areas I retrieved from multiple dates. Of course, in the notebook I mostly do plotting. I expect as a user you may want to do real analysis. Another example here is retrieving something for a point location. So you just specify your point. I use the aggregate spatial, but of course, when you're working on a single point, there's actually not much to aggregate. A point will always correspond to 1 pixel. So taking the mean over a point is actually just taking the point value. The time series from 2018 to 2021 included, returned here in about 14 seconds. And then, of course, yeah, I can plot it. You saw it already. So here I rather easily downloaded this multi-year time series. So the whole OpenEO code for that is really in those 2 lines. This is without any helper code or whatnot. So that's a point selection. Of course, you can do the same for polygon. And this here I specify my polygon as a feature collection. And you could also be specifying multiple polygons. In fact, what we are doing at Vito now, for instance, is even trying to do it for 100,000 polygons. The bottleneck there is that we cannot actually send this over the wire anymore as a feature collection. We need to point to a file that contains all of these polygons. But the code, in fact, remains mostly the same. So it's the same aggregate spatial, and then instead of the feature collection with 1 polygon, you have a lot more. It will run longer, of course. It won't finish in 20 seconds. It may take like an hour or more, but you will get this huge data set as a result. Here also we do something new. We don't request one statistic like the mean. We actually also requested quantiles and standard deviation. So we made the code a little bit more complex, but that makes sure that the OpenEO computes more than one statistic at the same time. And in this case, we also downloaded the result as a CSV instead of a netcdf for people who like to work with CSVs in pandas, for instance. Then you can plot it like you see here. So again, a multi-year time series. And yeah, this is the data frame where you can then again see that we really computed multiple statistics with this one column. Okay, this was some spatial aggregation that's relatively simple. In this last example, we want to make it a bit more complex by bringing the start of season into play. And we want to actually mask the seasonal trajectory with the start of season band. So this is an example that shows how to combine data sets in OpenEO. The start of season is loaded and we need to convert it to a binary mask. So we take the band and then take all values between two numbers here, and the numbers actually correspond to dates. And that allows us to really convert it into a mask. And then there's a mask function that we can use to apply a mask over a data cube. There's some extra stuff here. When we load the start of season, it still has a time dimension, but we want to ignore that. We just want to apply that mask to every instance. So we kind of get rid of the time by saying, okay, take the maximum over time. But if you only have one date, then that will select the one date. And we also need to align the cubes. That's what this resample cube spatial thing is for. So then again, yeah, it got downloaded, it worked pretty fast, and we can see that while before we had full images, yeah, now you see that there is a lot of no data in between because our masking worked. The last example I had here actually, yeah, then did another aggregate spatial over a bounding box, but that's not so interesting. One other thing I was playing with is that in the Python ecosystem, you can also use these kind of more interactive maps for your plotting. That's all nice, but that's of course not using OpenEO. One thing that is more interesting that I wanted to show is these were all fairly simple things, but you probably have used to more complex things in your daily work. For instance, phenology data can be very useful to use for classification problems. You may want to classify your pixels based on the phenology information. And actually, as part of the OpenEO platform, we did a use case on crop type classification. There, our features were not the phenology. We derived features from Sentinel-2 data, but the principle is actually would be very similar. You would take your phenology data from HRL, then extract, simply start of season, end of season. That would be your features. And then OpenEO, for instance, supports model training this is the rule-based training, a random forest-based model. So here, let me see, is it here? This is actually not entirely, here we have a prediction, but I'm wondering what this is based on. Let me see, because I may need to switch to this one. So actually, the thing is, if it loads, that the OpenEO actually also includes random forest-based training and then also inference. So it's actually, if I look for it here, we go ahead. Random. Oh wait, this is the offline classifier still. Yeah. Here it's offline, and here we do it in the UDF code. That's actually this part. So this is using custom codes, and we also have an integrated process. I actually hoped it was in this notebook, but it isn't. This is the how to do it with custom Python code, which is also possible. But that kind of wraps up really this very short demo. That's mainly to give you some idea of what can be achieved with the OpenEO integration of those layers. Okay.
Okay, thanks, Jeroen. Yeah, I think we found it important to show also this, let's say, newer technology in this webinar. As you have seen before, for instance, in the demonstration from Bert, to extract a time series and to plot basically the different layers, you had a large number of lines, Python code lines that you needed to program or execute. While here it's from a UI perspective or user perspective, I should say. It's very simple, like Jeroen showed, there's only like 2 lines, and you can immediately start playing around with doing different statistics on top of it, and doing temporal aggregation, spatial aggregation, whatever you would like. So that's I mean, the technology enables to put the data cube there. That's important. Then you can do all these operations on the data cube. And then at the end, I think, you showed also nicely that you can, move it forward and use, for instance, HR-VPP also, for instance, in machine learning techniques. That's all possible with this OpenEO technology. Of course, you need to have the platform, but I think there are more and more platforms who are becoming OpenEO aware or enabled at least, and then of course, from a user's perspective, you have to be careful because you need not only have a login. It will not be a free service at the end. I mean, you will need some credits at least to do your large scale processing. Either credits which are provided by bodies like ESA or other entities, or you need to buy the credits to run these kind of processes. But you see the power is it's a very powerful tool. I think that's what we wanted to demonstrate.